So now we'll take a look at graphing ellipses. The locus definition for the ellipse tells us that if we have a set of points and then we have these other 2 points, if the distance from that point to one point and the distance from that point to the other point add up to the same number, those points are on an ellipse. And one way you can think about it is looking at this diagram here, and you may have actually done this before in school. If you put 2 thumbtacks into a paper, let's say, and you take a loop of string, okay, so from this point to this point, put a loop of string here and pull it tight. The length of this string, the total length never changes, so this plus this is always the same. And as you drag the pencil around there, you will trace out an ellipse. So that's the locus definition for the ellipse. In terms of all the important characteristics, quite a few more even than the parabola. So let's take a walk through these real quick. This is how the equation, the standard form equation for an ellipse looks. We actually have a fraction over here with our x minus h squared. It's divided by a number called a, which is squared. And then our y minus k is also squared. And it's divided by a number b, which is squared. And everything is equal to 1. So we know that the ellipse is going to go left and right, sort of like this picture here, when we have x squared divided by a squared. Now how do we know which is a and which is b? And the way that we know that is that a is going to be the bigger number. So the ellipse goes left and right when the x squared has the bigger number for the denominator. This thing I'm calling a graph box. We'll see when we graph it, but basically we're going to start at the center and we're going to go a units left, a units right, b units up, and b units down, and those are going to define the sides of a box, and that ellipse is going to fit inside the box. Our center is at HK. We're going to have this number C, this going to help us to make those what we call focal points or foci, which are where our thumbtacks would go into. The vertices for a ellipse are going to be basically the endpoints along the long axis or the major axis, and then the co-vertices are the endpoints at the ends of the smaller or minor axis going this way. If we have y squared associated with or dividing the number a, which is the bigger between a and b, then we know that the ellipse is going to go up and down like this guy. Alright, so let's go ahead and do a completing the square example and see how we end up getting the standard form for the ellipse from this. So I'm going to go ahead and move the 4 over here to this side. Okay, so we've got -4 on this side. And then I'm going to do the same thing as I did before. I'm going to group my x terms together. And I'm going to group my y terms together. Oh, this is 36y. Okay. Minus 36y equals -4. Now, before I go ahead and start completing the square, I notice that I have a number in front of my y squared and in front of my x squared. In order for the process we had been using before to work, I can only have a 1 right here, not a -1, not anything other than 1. So what I'm going to have to do first is factor out this 4 and factor out this 9. And so kind of like what we did with the parabola, I have to take it from everything that I'm wanting to factor, which is everything in the parentheses. So I have to get the 4 out from x squared, and I also have to get the 4 out from 8x. Over here I've got the 9. I'm going to factor out from y squared, and I'll factor out from 36y. This is still -4 over here. So once again, we'll take a look at this. If I multiply 9 times y squared, I'm going to get 9y squared. And if I distribute the 9 into here to -4, I'll get the -36y. So this is why I have to pull out from each of the terms, because I'm basically undoing the distribution in this operation here. Now that I've got this piece and this piece with a 1 in front of the x and 1 in front of the y, I can go ahead and do my completing the square as I normally do. So let's see, negative 2 squared equals 4. And I'm going to go ahead now and go back to black, I guess. Here we go. 4x squared plus 2x plus 1 plus 9 times y squared minus 4y plus 4 equals negative 4. Now, I added my numbers on this side, and I have to add numbers over here, but this is another place you have to be careful. Look what happens if I redistribute these 4 and the 9 back into these quadratics here. I'm going to get 4x squared, I'm going to get 8x, and I'm actually going to get 4 right here, 4 times 1. I'm going to get 9y squared, I'm going to get minus 36y, and then here I've got an extra 36. Okay, so I've accounted for everything on this side, but I've got these extra numbers here. These are the ones that have to go over here. So two things when you're doing completing the square, when you have numbers in front of x squared and y squared. First thing you have to do is be sure that you factor out that number before you set up the square to be completed. And then once you do complete the square, you have to account for that factored number with the number that you put in there, okay, to add that to this side. All right, so continuing now, we're going to have 4. We know that this is going to collapse down to x plus 1 squared. We have 9 times y minus 2 squared. And then we have on this side, negative 4 plus 4 is 0 plus 36 gives us 36. Now remember, we want to get this into a form where we have these fractions like this equal to 1. And you may be looking, you may be looking at this thinking, well, this looks like a circle, and it kind of does, except you notice that these numbers are out here, and they're different numbers. If they were the same number, I could divide it out by this side over to here, and I would actually have a circle. And in fact, a circle is an ellipse. It's an ellipse that the two focus points are in the same place. But since these are different numbers here, I'm going to have to put this into standard form for the ellipse, which means I need to divide both sides by 36 to make this equal to 1. So I need to divide by 36 here, and I need to divide by 36 here. What this does then is gives me x plus 1 squared, and the 4 divided by 36 reduces to 1 over 9. Be sure that you understand this step right here, because that gives us our a squared term here. Same idea here. We're going to have y minus 2 squared. This 9 divided by 36 gives us 1 over 4. And then finally on this side, 36 over 36 is 1. And so this is going to be our standard form equation for the ellipse that we're working with right now. All right, so let's go ahead and analyze this in terms of the characteristics. I'm going to go ahead and put the standard form equation here just to have that for reference. All right, so easiest thing to do, of course, is to look at our x and y up here and figure out our h and k. So we've got h is equal to negative 1. We've got k is equal to positive 2. And we've got a squared is equal to 9, which means that a is equal to 3. B squared is equal to 4. And so b is equal to 2. Now if we go back to the characteristics here, we see that we have this other thing called c that we're going to need to get the foci, the focal points. So let's go ahead and calculate c. And c is square root of a squared minus b squared, so that's 9 minus 4, which is actually square root of 5. Our center will be at hk, negative 1 comma 2. We also need what's called the vertices. This is plural for vertex, so an ellipse has two vertexes or vertices. Okay, so these are going to end up at 2 comma 2 and at 2 comma negative 4. I'm not going to go through all the calculations for each piece of this. It's the same as what we had on the parabola before. You have to take each of the values, hk, a, and b, and put them into these formulas to get the x and the y for each of these characteristics. Okay, so we've got vertices, we've got co-vertices. Those are going to be at locations negative 1 and 6, and also at negative 1 and 0. And then the last is our foci, focus points, negative 1 plus square root of 5, comma 2, and negative 1 minus square root of 5, comma 2. Okay, so I have no idea what this number is as far as an approximation, which is what I'm going to need to graph it. So use my calculator, and I'm going to come up with about 1.24 comma 2 and about minus 3.24 comma 2, and probably even negative 3.2 and positive 1.2 would be close enough for graphing, but this is the idea at this point. You want to get an approximation for this so you can graph it. Alright, so let's graph this thing, and I think the best thing to do would be to start with the center. So we have the center at negative 1 and 2, so we'll just put a mark there. Now, from here what we want to do is make this thing that I'm calling a graph box. And the graph box is going to be a rectangle that is going to contain the ellipse. It's going to make it a lot easier to graph this. And so what we saw was that the graph box is going to have a width for a left and right horizontal ellipse. It's going to have a width of plus or minus a. And what we mean by that is we're going to start at the center, and we're going to go a units to the right. A is 3, so we go 1, 2, 3. And we're going to go a units to the left, 1, 2, 3. And if you notice, these are also the coordinates for the vertices. Okay, the major axis of the ellipse is running horizontal, and these are the endpoints of the ellipse. For the height of the box, we want plus or minus b. b is 2 in this case, so we're going to start at the center, and we're going to go up 2, and we're going to go down 2. And so the box is going to contain those points along its perimeter, and that would be the graph box. Now, in terms of drawing the actual ellipse, it's a little bit of a guessing game here, but kind of like with the circle. Take your time and make something kind of ellipsified looking. Okay, not very perfect, but again, you kind of get the idea here. Now, the other points that we need to plot are these foci, the focal points. And so I'm going to have two of these, and one of them was going to be at 1.24 comma 2. So 1.24 roughly around here, comma 2, roughly about here. And then negative 3.24, 1, 2, 3.24, right about here. So the focal points are going to be symmetrical to the minor axis. And so these look like they might be more or less in the right place. So this is how you do the left-right ellipse. And if we look at a computer-generated plot, we've got something very similar.